In this video, we're going to talk about how to solve some basic, simple harmonic motion problems in physics. So let's start with number 1. A horizontal spring with a mass of 0.75 kilograms attached to it is undergoing simple harmonic motion. Calculate the period, frequency, and angular frequency of this oscillator. So if you want to try this problem, feel free to pause the video and work on it. The formula that we need to calculate the period is this equation. It's equal to 2 pi times the square root of the mass divided by the spring constant, which we have all of that in this problem. So the mass is 0.75 kilograms, and the spring constant is 300 newtons per meter. So let's go ahead and type that into the calculator. So the period is 0.3142 seconds. So that's how you can find the period of a simple harmonic oscillator. All you need is the mass and the spring constant. Now part B, what is the frequency? Frequency is 1 divided by the period. So it's 1 divided by 0.3142 seconds. So the frequency in this problem is 3.183 hertz. Now let's move on to part C. Let's calculate the angular frequency. The angular frequency represented by the symbol omega, it's 2 pi times the frequency. So that's going to be 2 pi times 3.183 hertz. And so that's going to be about 20 radians per second. And that's it for this problem. Number 2. A force of 500 newtons is used to stretch a spring with a 0.5 kilogram mass attached to it by 0.35 meters. What is the value of the spring constant? And calculate the frequency of the oscillator. So let's say this is a wall, and we have a spring attached to it. And there's a mass. Now we're going to stretch the spring using a force. And so this is a 0.5 kilogram mass. And at this point, we're applying a force of 500 newtons to stretch it by 0.35 meters. So how can we calculate the spring constant? Well, we know that the force is equal to kx based on Hooke's law. So the spring constant k is the ratio between the applied force and the amount that the length of the spring changes. So it's going to be 500 newtons divided by 0.35 meters. And so that's going to be 1428.6 newtons per meter. So that's how you can calculate the spring constant of a spring. It's simply the force divided by the change in length. Now let's calculate the frequency of the oscillator. The frequency of this spring is going to be 1 over 2 pi times the square root of k over m. So it's 1 over 2 pi times the square root of the spring constant, which is 1428.6, divided by the mass of 0.5. So the frequency is 8.51 hertz. And so that's the answer to part B of that problem. Number 3. A spring with a constant of 100 newtons per meter vibrates at 25 hertz. What is the frequency of vibration of a spring with a constant of 400 newtons per meter? So what happens to the frequency if we increase the spring constant? As the spring constant increases, the frequency increases. And we know that the frequency of a spring is 1 over 2 pi times the square root of k over m. So notice that the frequency is proportional to the square root of k. And in this example, the spring constant increases from 100 to 400, so it increases by a factor of 4. And the square root of 4 is 2, so therefore the frequency should increase by a factor of 2. So the answer is 50 hertz. Now, if you want a formula for this type of problem, here's how you could derive it. Since we're dealing with two frequencies, let's write a ratio between the two frequencies, f2 and f1. So f2 is going to be 1 over 2 pi times the square root of k2 divided by m. f1 is going to be 1 over 2 pi times the square root of k1 over m. Now, I didn't write a subscript for m because the mass doesn't change in this problem, so we could cancel it. And at the same time, we could cancel 1 over 2 pi. So thus we have this expression, f2 divided by f1 is equal to the square root of k2 divided by the square root of k1. Or we could just simply write it like this. f2 over f1 is simply the square root of k2 over k1, all within a single fraction. So now let's calculate f2. So f1 in this problem, that's 25 hertz. And that corresponds to a spring constant of 100. So k1 is 100 in this problem. We're trying to find a new frequency at this new k value. So k2 is going to be 400. So 400 divided by 100 is 4. And the square root of 4 is 2. So f2 over 25 is equal to 2. Now let's cross multiply. So f2 times 1 is simply f2. And then we have 25 times 2, which is 50. And so that's the new frequency. So if you have a problem that relates frequency to the spring constant, you could use that formula. Now let's work on this problem. A 0.75 kilogram mass vibrates according to the equation x is equal to 0.65 cosine 7.35 t. Determine the amplitude, frequency, period, and the spring constant. So x represents the position of the oscillator. So let's say the oscillator is at equilibrium. It's right here. So right now the position is x equals 0. It can oscillate this way and that way. So here x could be 1, and here x could be negative 1. It could be 2, it could be 3, it can vary. The amplitude is the maximum displacement for the spring. So let's say if the most that the spring will stretch to is up to this line, and let's say that's 1.5. And so the most that it can stretch to in the other direction will be here. So in this case, the amplitude, the maximum x value, is 1.5. Now x could be anywhere between negative 1.5 and positive 1.5. So x represents the current displacement. A, the amplitude, is the maximum displacement. So make sure you understand the difference between the two. Now, you need to know the generic form of that formula. The current displacement is equal to the maximum displacement times cosine omega t. Now sometimes you may have a phase angle, but we don't have it for this problem, so all we have is this formula. So the amplitude is whatever number you see in front of cosine. So the maximum displacement is 0.65, which means that x can be anywhere between negative 0.65 and positive 0.65. So if you graph this cosine equation, the amplitude is 0.65 and negative 0.65 on the graph. And cosine starts at the top. So the cosine wave is going to look something like this. And it's going to keep oscillating between these 2 points. Now, what does this number represent? 7.35. Notice that the variable in front of t is omega. So the 7.35 represents the angular frequency of this oscillator. So it's 7.35 radians per second. And if we know the angular frequency, we can now find the frequency. The angular frequency is equal to 2 pi f. And so 7.35 radians per second is equal to 2 pi times the frequency. So the regular frequency is just 7.35 divided by 2 pi. And so you should get 1.17 hertz. Now, how can we calculate the period? If you know the frequency, then you know the period. The period is simply 1 over the frequency. So in this example, it's 1.17 hertz. It's 1 over 1.17 hertz. So 1 over 1.17, that's 0.855 seconds. So we have the amplitude, we have the frequency, and we have the period. So the last thing we need to calculate is the spring constant. So what formula can help us to do that? Well, we know that frequency is 1 over 2 pi times the square root of k over m. So the first thing I'm going to do is multiply both sides by 2 pi. So I can get rid of this. So on the left I have 2 pi f, and that's equal to the square root of k over m. Now I'm going to take the square of both sides to get rid of the radical on the right. So I have 2 pi f squared, and when you combine a square and a square root, those two will cancel. So on the right, all I have is k over m. So I'm going to multiply both sides by m. So let's get rid of that. So the spring constant is equal to the mass times 2 pi times the frequency squared. So if you have the mass and the frequency, you could use that equation to calculate the spring constant. Now keep in mind that omega is 2 pi f. So we can replace 2 pi f with omega. So the spring constant is the mass times the square of the angular frequency, which we know it's 7.35. So we have a mass of 0.75 kilograms multiplied by 7.35 radians per second squared. And so the spring constant is 40.5 newtons per meter. And so that's the final answer for this problem. So hopefully this video gave you a decent understanding of all the formulas that you need for solving basic simple harmonic motion problems. Thanks for watching.